time. Uh, yeah, so today is going to be packed. So the first thing I want to do is actually explain like the most technical part about this stuff that we're going to be doing. And that's actually about the justification. So I want to make the justification process like really clear. Like what is it that we're trying to do here? Because all of these problems are optimization of some kind. And so we still have the same process of taking the derivative of the function, setting equal to 0, solving, and all that. But the previous methods that we showed you, the closed interval method will work for these. But the first derivative test and second derivative test that you learn, those are for those will indicate for you that you have a local min or max. And the key thing is that there's a difference between a local and a global or an absolute min or max. So what we are trying to do for all of these problems in our problem set from 6 to 11, all of these, is it 6? Yeah, 6. Oh. 10, 11, okay, yeah, 6 problems. Yeah, in these 6 problems, it's all about absolute mins or maxes. And so we are going to need potentially some slightly different approaches. But the first thing that you can use is the closed interval method, which we have used in previous problems, where you know that a function is defined on a closed interval from A to B. And what you would do is you would end up finding critical points inside that interval, and you would test your function at the endpoints and at the critical points, and you would see you just pick out like the maximum value or the minimum value, and you would know that that is the absolute min or max value because all of the all the possibilities are listed there. So closed interval method is one of the approaches. But then there's the issue of what if the interval that you have isn't a closed interval? And the common example is what if that interval is 0 to infinity? So we'll see actually 2 problems that have that as our interval. But overall, there are two methods. I'm going to copy some of the information about them from the slides. And these are the first and second derivative test for absolute extreme values. Okay. And I'm going to try to explain like what these are about and just how do they differ from the first and the usual first and second derivative tests. So the wording is something you have to be very aware of. So notice in this first derivative test, it's saying for all x less than c and then for all x greater than c. So first of all, that for all is actually a for all on a domain. It's actually talking about in terms of some defined interval. But what the property is actually trying to say is that you don't have any other critical points show up in your say you're in your sign chart. So like normally what you would do is you create some sign chart and you'd see like this plus or minus. And then the standard first derivative test is actually only looking at the immediately adjacent areas around C. It's only looking to the left and to the right. And it says nothing else about like whether or not there are extra other critical points. But this first derivative test for absolute extreme values is saying that not only do we have this kind of signature, but we don't have any other critical points. The fact that we don't have any other critical points is the key thing that lets us say that whatever this thing is, which, well, in this case, this is actually a local max, right? If there are no other critical points, then we can then actually conclude that not only is it a local max, it is an absolute max. And the reason why this would make sense intuitively is that by asserting there aren't any other critical points, we're saying that like the increasing decreasing kind of behavior of the function doesn't change. So it doesn't just like it forces the shape of the function to be like that. You don't have any other kinds of dips. Like you don't have it sort of like create a valley afterwards. Like if it starts to like if it changes in the way that its direction is moving, that would give rise to a critical point. And this assertion is saying there aren't any other critical points, so there is no change in the directionality of the function besides the critical point that we have there. Okay. The second derivative test is also it's about this kind of for allness here. So yeah, we see that it's saying something about the second derivative being less than 0 for all x. And again, this for all x really it means for all x in the domain that we're considering. But yeah, and that is useful because like if we're considering an interval that isn't closed, so like if it's an open interval, we can just restrict ourselves to that open interval, just use this property, and that'll conclude for us that the c value is. Actually, there's a very important distinction here as well. So if you recall what the second derivative test is actually saying, what the second derivative test does is you plug the critical point that you're testing against into the second derivative, and you see is the value positive or negative. Notice that this is not saying we're plugging in the value c, it's saying for all x. So this is actually like quite different, right? If you just plug in c, you're asserting something about like the local, like that is local to c, that is near c. But when we're saying for all x, we're actually talking about something that's global. We're talking about something that occurs on this entire range of possible values of x. So, yeah. So see that there's like a subtle difference there. All right. I think that's all I can really say about this. So, let's get started on the problems, unless there are any questions. No questions? No, everyone's okay. All right. Right. Then let's get started. Yeah, so I'm gonna have to like speed up near the end probably, but I'll try to be very slow at the beginning. Right. So in this problem, we want to maximize revenue. We're given this price function. So the revenue is going to be given by multiplying the price function by whatever price we're charging times the number of cakes that we end up selling. And so this revenue function is going to be 75x minus x cubed over 4. And we would want to optimize this thing. So just like how we normally do, take the derivative, set equal to 0, and solve. 3 over 4x squared, which we would set equal to 0. And when we solve this guy, we're going to get that x is equal to plus or minus 10. But clearly, x should not be a negative number. X is the quantity of cakes that we're selling. So we would take the positive part, and let's think, what are we actually asked to figure out? What cake price will maximize the revenue? Okay, well, x is the number of cakes. So if we want to figure out cake price, we have to actually plug this back into P. All right, so that's one part. But another thing is, how do we know that this is corresponding to maximizing revenue? So we have to do a little bit more work on that. The normal thing we would do is we would actually, like, you could think about doing a sign chart just to orient yourself on how this problem works. And if you do that, you'll get this. So that tells us that 10 is, at minimum, it is a local max. So we know that it's a local max. Great. We want to make sure it's an absolute max as well. So it would be really helpful here is if we can establish some kind of closed interval, because for this problem, we actually can. Okay. So the key thing to think about is like, how do you, what would be a nice like value that would just like in previous problems, what we tried to do is we tried to like degenerate a rectangle. Here we can also do that kind of same idea. We can degenerate something. In particular, we can look at this product and we can say, what if we let x equal 0? Well, that's going to make the revenue equal 0. So that's a really easy value to use. All right, so if we plug in 0 into the revenue function, we're going to end up with 0. And we want some other endpoint also to end up equaling 0. And we will then also want to plug 10 into the revenue, and we want to see that that is going to have a positive value. Therefore, it'll maximize the revenue because it'll be the highest value on this list of candidate values for absolute maximum. Well, the other thing we can do is we can make this p of x equal 0. Once that equals 0, then we know this is going to equal 0. So how do we make p of x equal 0? Well, just go ahead and try solving this thing. P of x is this 75 minus x squared over 4. So we want 75 to equal x squared over 4. Multiply by 4, we're going to get 1200, I think. Or, no, not 1200. 12 times, oh yeah, 12 times 25, so that's going to be 300. Yeah, okay. And so then x is equal to 10 root 3. So the closed interval that you would use is this 0 to 10 root 3. And we can just conveniently picked values for which we knew that the revenue would be equal to 0 because that's just the easiest thing to do. Okay, and then lastly, we'll plug in 10, right? So 10, if we plug that in, we're going to get 750 minus, or no, wait, 10, 10, 250? Yeah, 250. Yeah, because 1,000 divided by 4. And then that's going to be 500. Okay, so revenue is 500. So this is the closed interval method that we just performed. So yeah, this finds for us that this is the x equals 10 is going to correspond to an absolute maximum for revenue by the closed interval method. But if we read our problem again, we'll see that the problem actually wants, it does want us to maximize revenue. So we said that, we asserted that this was going to maximize revenue, but we want to actually answer in terms of the cake's price. So, and notice that x is not the cake's price, x is the number of cakes. So it's a bit, the way that this problem is structured is a bit funny. It's a bit more work than, I don't know, it feels a bit funny, but it makes some sense. So what you actually want to do then is you want to figure out what is P of 10. All right, the cake's price is P of 10, which is going to be 75 minus 25, which is equal to $50 per cake. So this is the cake price that's going to correspond to maximizing revenue. And so that's the answer. But your answer also needs to include some kind of justification. So I guess you could box that part maybe as well. All right. So did that process make sense? Any questions?
So I just justified it by saying that it's just concave down, that the whole graph basically is just concave down, so there's only one absolute max that way. Does that work as well?
Concave down. It depends on how you did that. So did you take a second derivative?
Yes.
Okay. And then you said something about by common sense, x has to be a positive number.
Yeah.
Great. Yeah. So yes, that will do it. Mhm.
Okay. Okay. Sweet.
Yeah. Yeah, because you have to do that domain restriction. Otherwise, technically what you're saying is not correct. But here, yeah, x has to be positive, so that'll work. Mhm. Yeah, very good. And I would actually, instead of just saying concave down, it's probably better to appeal to this. What you're really doing is you're doing this without realizing it. Does that make sense?
Yeah, that makes sense.
Mhm. Yeah. Yeah. So like I said, like these two properties are really showing that this thing looks like a parabola, which is pretty much exactly what you were saying about the whole concavity. Like, yeah, the shape of the function, it doesn't go up. It doesn't change more than one time. Okay, very good. Let's keep going. So 7, maximum area of a triangle with hypotenuse 1. So we have a triangle, and I'm going to label one side x, the other side I will get from the Pythagorean theorem, square root of 1 minus x squared. We want to maximize the area. So area is 1/2 base times height. So that's this guy. And that looks kind of terrible because we have to take a derivative of it to optimize it. But that's the only thing we can do. So I'm just going to force us to think of this as a function. So 1/2 1 minus x squared plus 1/2 x times 1/2 square root 1 minus x squared times minus 2x. Right. And for this problem, at least I could probably do all the algebra with you, but I won't be able to do that very soon because of time. So what I will do is I'll put everything over I'll pull out a 1/2. I'll put everything over a common denominator of 1 minus x squared. And notice that that means I'm going to end up squaring this thing in the square root. For the first term. And then the second term, when we collect the things, we're going to end up with negative x squared. So we have another minus x squared on top. And so that's how we would simplify that. And this, I can just clean this up a little bit. I actually put it over the, yeah. Okay, and we go about the process of optimizing this. So set this equal to 0 and solve. So when we solve, 1 equals 2x squared. And so then x is equal to 1 over the square root of 2, plus or minus, but we know that it's got to be the positive version since this is a side length. Okay, right. And now the thing is, this also has a convenient closed interval that we can think about, and so that'll make calculation a bit easier. So because what we can see is that we can actually make this triangle situation degenerate. If we let x be equal to 0, then this is going to correspond to just a vertical line segment. So, and if x is equal to 1, this is going to correspond to horizontal because like we just kill off one of the directions. We make it so it doesn't go vertically at all, or it doesn't go horizontally at all. It doesn't have that option. So yeah, either of these two endpoints are going to have the area be equal to 0 because you don't have a triangle anymore. Okay, so we have that, which is really great. And 1 over root 2 lies inside. It's like 0.7 something. Yeah. But so now we try to plug that in, and I'm just gonna say, well, you should be able to do the computation by hand, but I'm going to suppress that for time. So that's you're gonna get 1 over 4, and clearly that's the highest number on this list. So this is the absolute maximum. And so what are we doing? Absolute maximum value for area, and the reasoning is by the closed interval method. I think that's all I needed to do for that. Yeah. Okay, so that makes sense. Okay. Not hearing anything. Fine. For number 8, we've got a box. Okay. So I always like to draw a sketch just to see what I'm dealing with. All right. So that's a box, and it has a square base. So let's call the base is of length x, and we'll have a height as well for h. The 12 square feet is talking about a surface area. And so that's x squared plus 4xh. We count the base, we count the 4 sides around it, we don't count the top because there is no top. And we want to maximize volume. Okay, well, volume in this case is x. Oh, I should say this is equal to 12 feet squared. Volume is equal to x squared h. And we're trying to optimize this function, or yeah, this function. Well, the thing is that this right now is a function of 2 variables, so we can't optimize it in this way. We need to get rid of one of the variables. And we get rid of one of them by using the first equation. So if rewriting this, I'm going to get 12 minus x squared divided by 4x equals h, just solving for h. So I now have an expression for h. I can then replace h out. Okay, so volume is going to end up being 12x minus x cubed over 4. And I can split that to make derivatives a bit easier to think about. X cubed over 4. Okay, so now we have volume as a function of x, and now I can optimize. So I take the derivative, squared. Yeah. I would set that equal to 0, and I would solve. Solving, it's going to give me 4 is equal to x squared, so x is equal to 2, and this is in terms of feet. Okay. So it actually gives you plus or minus 2. That would matter if like you were to, where's my cursor? That would matter if you were to draw out the full-on sign chart of that. You'd have minus 2 and 2, and then you'd see it's alternating, and it's negative here. Right. But for this problem, it actually turns out we can use closed interval method yet again. Okay. So usually I would use closed interval method if I can. Otherwise, I'll try to use one of the other techniques. It's just a bit easier to argue it. So here, like, notice like what we can do to make this situation degenerate is if we let x be equal to 0, then clearly volume is going to equal 0. Okay, so yeah, so 0 is one of the points of our closed interval because volume with x equals 0 is going to be 0. And then the questions asked is like, what's the other endpoint? So that's going to involve making h equal to 0, right? We can kind of just look at this volume function here and we say, okay, either this x squared equals 0 or this h equals 0. How would we make h equals 0, like graphically? Well, what happens is like all of the material ends up being used for the base, and we have no material left over for the height. Okay, so that's saying that x squared is going to be 12 feet. Okay, we can just take the square root of 12 then, which means that, what is it? No, 2 square root 3. 2 square root 3 being the other endpoint. So that's just the square root of 12. Yeah, and that's going to make the volume equal to 0 as well. And then lastly, we can calculate what would the volume be for 2. So I would just plug that into, I guess, this guy. We would get 6 minus 8 over 4, 2. We get 4 feet cubed. And so we see that this is the maximum of all these. And so then this is the absolute max by the closed interval method. And make sure I'm answering the original question. Find the largest possible volume. Yeah, absolute max value for volume. Okay, so that is that problem. And 9 is where things change up a little bit. So for 9, we're going to end up finding that we can't use the closed interval method, and we're forced to use some other approach. Let's see. Volume is 8 meters cubed. We again have a rectangular rectangular prism kind of situation with a well, it's a square prism. The base is square. Okay. So again, I'll use x's and h's, and we are talking about cost. Okay, so cost is 1 per meter square for the base and 4 per meter square for these sides. So that's going to be 4 times 4xh. Yeah. So one of these 4s is because there are 4 sides. The other 4 is because the cost is $4 per meter squared. So this is the cost function. And just like before, we need to get rid of one of these variables in order to optimize. So I had to use the other equation, which is that 8 is equal to x squared h. So let's just divide to get h alone. And now I can replace out h. X squared plus 16 times a divided by x. Right, so I now have the cost function. And I can take its derivative. I actually have this value written, but I don't know if I really need it. I just write it. It's 256 over x squared. And so like usual, set this equal to 0, and we would solve. So here, one thing I would want to sort of warn you about is that if you were to move the fraction to the other side and multiply by x squared to solve, implicit in that, what you're doing is you're assuming x is not equal to 0. And so that approach has a tendency of making you forget about one of the critical points, which may matter in some problems. For this problem, it doesn't matter so much, but there are certain problems where that would matter. So I'm going to show you the other technique, which is that you actually combine this into one fraction. So 2x cubed minus 256 over x squared is equal to 0. And then you're supposed to reason about this function from here. So it's more easy to see that x equals 0 is corresponding to like the derivative being undefined. It's a critical point in that sense, right? Otherwise, yeah, then we would have x cubed is equal to 128. Is that right? 128. Oh wait. This is not 256. This is 128. The other thing is 128, 128, and this is 64. Yeah, powers of 2. Okay. And so this x is equal to 4. Right. Yeah, so the reason I say that is like if you ever are relying on that kind of thing and then you're tabulating a sign chart, that's going to correspond to like missing one of these critical points and then possibly messing up the sign chart and everything thereafter. So you want to be careful for that. But here we actually don't really do it, I think. Here instead, well, if we just think about this a little bit and try to like reason about like what is a natural interval, you'll see that in fact it's not a closed interval. For this problem, the natural interval for like an x, if you just stare at it, you end up realizing it's 0 to infinity. Because the idea is that the only real condition that we have is that the volume must equal 8. Well, there's a lot of different ways to make that happen. In particular, like what we can do is we can kind of x and h kind of are reciprocal in their contribution. So if like I make x really large, I can make x really tiny to cancel out the factors and force the volume to equal 8 still. Like x can be 100 if it wants to be, as long as I make h like 0.00 something. Conversely, x can be really close to 0, really a really tiny value, so long as h is really high, and I can still force that the volume be 8. And so that's why we end up with this kind of interval. We don't have a closed interval that we can naturally use to enforce anything. This is the key distinction between problems 8 and 9. You can kind of see also like there's sort of a flip in what happens. With number 8, we're told a condition about the surface area, and we're trying to optimize volume. Here, with number 9, we're given volume, and we're trying to optimize surface area. We can kind of think of cost as like a weighted version of surface area. So like just by flipping that, we end up having a pretty different situation and we have to approach it differently as a result. So what we can do here to make things easier is actually, well, since this is the thing is that since this 0 to infinity is our natural interval to think about, that's going to get rid of that 0, this critical point here. So we actually don't need to consider that. And with that, we could argue by first derivative test, like there aren't any other critical points on this domain. Therefore, this thing, which is a local min, must actually be an absolute min. We can totally do that. I'll do the second derivative test instead, just because like in this case, in this problem, it's not so hard to take a second derivative. Just look at this function. All right, I can just easily take that next derivative. I get 2 plus 128 or times 128 times 2 over x cubed. And well, as long as x is positive, this whole thing is going to be positive. Right. And so since this is true, we can then conclude that x equals 4 is going to correspond to the absolute min for the cost function. And the reason is by the second derivative test for absolute extreme values. I'm just going to abbreviate that for sake of time. Okay, and then lastly, like this problem is actually asking us to find the dimensions that minimize. So we want to write our final, I guess, answer in terms of the dimensions of the box. So it's going to be 4 by 4 by a half. And the problem is in terms of meters. Let me talk like 4. Okay. So yeah, hopefully that's okay. Interrupt me if you have questions. Otherwise, we're going to go a little bit over time. So sorry about that. 10 is really nasty, to say the least. You're supposed to probably do this by hand, and I'll just say like almost definitely like you're not going to be given a problem quite as convoluted as this on the exam, but it's good to be able to do this kind of thing by hand. It's always good to do a slightly harder problem than usual. Okay, so I'm going to label things x and y, and this radius. Do I even use this radius? I don't even know. 1/2 x. We're told that 10 feet of framing are given to us, so that's a perimeter. Okay, so this is x plus 2y, and then plus the portion of the perimeter corresponding to the half of the circumference of a circle. So circumference of a circle is pi times diameter. In this case, pi times x would be for the full circle. We have to have that, so it's 1/2 pi times x. Okay, so this is the equation given for the perimeter, and what we want to do is we want to maximize the area. Okay, so I need a formula for area. Well, that's x times y, and plus half of a circle. So 1/2 times pi r squared. Pi times r squared. R is going to be the x over 2, so we have x squared over 4. Okay, and this is where I really am going to need to suppress quite a bit of algebraic calculation, but you should be able to fill it in on your own. Like with the previous problems, we need to get rid of one of these variables so that we can optimize this function. And the variable to get rid of is really the variable y. So we would rewrite this upper equation so that we have y equals a function in terms of x. And I'm just going to shortcut to what that function is, skipping all the algebra that you should supply on your own. So you should get that. So you can did I combine? I did combine. Let me combine that fraction. I should have looked one line down. So you'll get that as your function for y, and then you replace, and then you do. So I'm just gonna put some dots to say like, oh, you should fill in those dots. You substitute, do some algebra. You'll get a as a function of x is equal to 5x. Can I say minus? Yeah, I'd rather say minus. Yeah, I don't know why I put that like that. Minus pi plus 4 over 8x squared. So then we can take the derivative, get 5 minus pi plus 4 over 4x, and we would set that equal to 0, and we would solve. And when we solve, yeah, okay, this one I claim you can just do this in your head. So that you get 20 over pi plus 4 is equal to x. And this is in terms of feet. And just like with all the other problems, you would want you would suppose that this should correspond to the maximum of the window area, but you have to justify that claim, right? So the easiest way to justify is take yet another derivative. Look at how easy that thing is. You just take another derivative, right? Where's my cursor? A double prime, take a derivative, negative pi plus 4 over 8. That negative is in front of the whole fraction. Sorry about that. Yeah, so pi plus 4 over 4. This is a negative number. It's less than 0. Therefore, therefore this is that condition is going to be the place where an absolute maximum happens. The absolute this is an absolute maximum by the second derivative test for absolute extreme values. And lastly, for this problem, notice it wants you to find the dimensions of the window. Okay, so just having this x value, I would say, is not enough for the dimensions. You also need to know this y value. Right. I should have said in the beginning that also this is a rectangle and not a square. This may look like a square, but if you read the problem, it says rectangle, and so that's why, like, to set this problem up, you have to start off with that with this assumption that these two variables are not the same. All right. Okay. Right. So then, how do we get the y value? Well, we take this x value, we plug it into this equation here. Okay, and then that's gonna involve yet more calculation. You end up with y is equal to 10 over pi plus 4 feet. Okay, so those two answers combined, that's going to correspond to that's going to correspond to answering in terms of the dimensions. Okay, so yeah, any questions on that? I hope that, like, you should see at least, like, you should be able to do the algebra. You should be confident that you can do the algebra. Right. Everyone okay? All right. Right. Then lastly, we've got number 9. Okay. Well, so with number 9, first thing I want to mention is actually these units. They're a little bit awkward. 100 of pounds, 100 pounds, 100 pounds, and 100 pounds. It turns out that this is fine. We don't need any unit conversions or anything like that, but it's just something you need to check, right? Yeah. So first of all, we've got this expression for weight, and we're told that we want to minimize the cost of raising a hog of this particular weight if corn costs something and soybeans cost something. Um, well, if the weight is that, then we can just plug that into this W function because this is W. And that's going to give us an equation. But then if we think about it, we're trying to minimize the cost, right? So cost hasn't factored in yet. Cost is something else. And it's going to be 6 times 100 pounds of corn. 100 pounds of corn is X. And then 15 per 100 pounds of soybeans, which is Y. So the cost function is actually this. And like with all the other problems, we want to get rid of one of these variables. So we look back on our first equation and we reduce things a little bit, not 55. So what turns out to be really convenient for this problem is if we can just raise both sides to the fourth power, that would just get rid of these nasty square roots that we have on this right-hand side. So we just think about this in terms of squaring it twice. Okay, if I square it once, I'm going to get 25 is equal to x, y to the half power. Right? If I just square it once, and I square it one more time, 625 is equal to x squared y. Great. Now I can easily see that y is equal to 625 divided by x squared. So then I can plug that in. 6x plus 15 times 625 divided by x squared. So now I have cost as a function of x, and I can optimize. Not putting plus, it's minus. Minus 15 times 625 times 2 divided by x cubed. Right. Then we would set this equal to 0 and solve. In this case, I would just do the naive thing and just bring it to the other side, multiply, and then divide. So we would just have like x cubed is equal to 625 times 5, if I'm not mistaken. Yeah, I'm pretty sure that's right. Yeah, that's right. Okay. But then we take a cube root of that, which is interesting. So this is actually x to the 5 over. This is actually x to the 5th power. 625 is 5 to the 4th power. 5 to the 5th. So this is x. X is then 5 to the 5 over 3rd power, which is the same as 5 times the cube root of 25, which might be a bit more comfortable looking for you, and I think it is for me as well. Now, and we would think that like this ought to be the thing that will optimize this cost function, minimize the cost function. Okay, let's go ahead and also calculate what the y value is. Just so that's just another calculation that you do. So I probably want to supply some more details to this. Y ends up being the cube root of 25. And these are in terms of hundreds of pounds. Yeah, maybe you want to say that. What is find the values of x and y? So the problem wants us to find values of x and y, hundreds of pounds. All right, so I don't know, something like that, just to deal with units. And right, so lastly, we want to justify that this is the absolute minimum for the cost. Taking a second derivative is the easiest way to do that for this, because notice that second derivative is going to get rid of the 6, and then the sign is going to flip to a plus, and x to the negative 3rd is going to turn into x to the negative 4th. which is good because that's going to square things out. So you know that's going to be positive. So second derivative, I'm going to do just as I said, 15 times 625 times 2 times 3. If you really wanted to, you could totally multiply that, get a number. I just care that it's a number that's positive. So this whole fraction ends up being positive. So the second derivative is positive for all x, effectively. Well, we really is for all x, except for 0, but it's fine. And so that means, well, concave up, hence this is an absolute minimum. Absolute minimum. And the reasoning is by the second, why am I writing that out in words? By the second derivative test for absolute extreme values. Okay, so that's our justification. That's why we know that this corresponding x value, which gives rise to this corresponding y value, why does this correspond to a minimum, an absolute minimum for cost? Well, it's by the second derivative test. Okay. So, are there any questions? Anything you want to go over? I can spend a little bit more time since I know this is possibly a more tricky subject. No questions? Okay, then we'll end it here.